Okay, welcome back everybody. This is the final session of the day. We've got a great panel to round out the excellent presentations we've had today. My name's Joe Applegate. I am a professional geologist and department manager for the Tallahassee and Pensacola offices for Geosyntec. Originally was at DEP and have been in the industry for about 40 years, and I've been grappling with PFAS with the rest of you over the past 5 or 10 years. We have a very distinguished panel in this session that we're going to be talking about advances in source management, treatment, and destruction technologies. I did want to recognize some of the excellent presentations we've had today on the State of the Union of PFAS, legal and regulatory updates for Florida and federal programs. And of course, yesterday we had Michael Goldstein, Tori, and others, Rob and Neely, on the update on PFAS and biosolids and wastewater. Wastewater is not my favorite subject, but it's a solid number 2. That's number 1, okay? So last year I was going to tell a PFAS joke, but I didn't think it would stick. That was a pretty good one too, right? Anyway, all right, well, we'll get started so we can all get to happy hour sooner rather than later. So our first speaker today is Flore Martin. She's an environmental engineer and project coordinator with Veolia North America, and she's going to talk about incineration at Hazardous Waste Incinerator.
Good afternoon. So today I will present you the results of the PFAS testing that we performed at one of our hazardous waste incinerator located in Port Arthur, Texas. It's a hazardous waste incinerator that usually treats about 70 kilotons of waste annually. And so we decided to perform a PFAS testing last year in 2 rounds. So we did the first one in July. We tested 2 different PFAS matrices. And then we did the next one in October, and this time we tested 4 different PFAS matrices. And we wanted to do this test because we wanted to answer 3 main questions. The first question was how efficient is high-temperature incineration to destroy PFAS, and in particular, how efficient is Port Arthur, our incinerator. We also wanted to know what was the probability when we are incinerating PFAS to release PFAS via solid or liquid residues of incineration, or even via air emissions. And finally, we were really interested to know if when we incinerate PFAS, do we completely destroy them, or are we creating what we call product of incomplete combustion? So product of incomplete combustion, or PIC, it's when you turn a long-chain PFAS like PFOS into a short-chain PFAS because it's not completely destroyed in the incineration process. So a quick word about our protocol. In July, we tested 2 different matrices. The first one was AFFF. We did 3 runs. And we also incinerated contaminated soil, 3 runs too. Then in October, we had 4 matrices. We retested AFFF incineration, but this time we did 1 run with lime injection during AFFF incineration and 2 runs with that. The goal was to study if adding lime during PFAS incineration would somehow impact PFAS degradation. We also incinerated contaminated soil again. And then we tested spent carbon contaminated with PFAS and CF4. So CF4, it's not a waste that we usually receive at Port Arthur. We wanted to incinerate it because we knew that the EPA was interested in the destruction of CF4 in a commercial hazardous waste incinerator. Because CF4, we will focus on it later, but it's an ultra-short PFAS, only 1 carbon, and it's supposed to be really hard to destroy. So, of course, we respected the EPA's guidance regarding our protocol and testing. The incinerator was operated under normal conditions during the PFAS testing. So the temperature, it's above 2040 Fahrenheit in the second combustion chamber, which is like the second step of the incineration process. And another key parameter, it's the residence time for gas. At Port Arthur, it's around 2.3 seconds. And while we were incinerating the PFAS, we were also injecting regular waste without PFAS, as usual. We just put a ban on PFAS with a high F content. Now, before each new matrix, we would do what we call a baseline run. It's when we incinerate waste, no PFAS, but we still sample liquid, solid residue, and air emission, and we look for PFAS in these samples. That's like the blank level. And we systematically, after each run or during each run, we were sampling all the liquid, solid residues from incineration and air emission at the stack. So we have 3 solid samples, ashes from the kiln, slag, and filter cake from the water treatment line, because we have a wet flue gas treatment. We had only 1 liquid sample, which we can call blowdown. And at the stack, we were doing OTM45 and OTM50 and HF sampling. So OTMs, there are 2 methods developed by the EPA to sample PFAS in air emission. So we didn't do the stack testing ourselves. We asked AECOM, which is a famous stack testing company, to do it. I'm going to start with the liquid sample results because we find some interesting data from the beginning of our test. So as I was saying, we sampled the blowdown at the end of each test, but we also sampled the site water that we use in the incinerator. Because as I was saying before, we have a wet flue gas treatment, which means that after the incineration process, the flue gas is in contact with water. And we sampled this water. And we found out that even before we inject the water in the incinerator, this water is already contaminated with PFAS at low level, PPT level, but still. So this water, we take it from a pond nearby the incinerator, and we discovered, as it's the case for many water sources in the US, that it was contaminated with PFAS. So of course, if we have PFAS in the site water that we inject in the incinerator, we expect to have some PFAS in the liquid residue. And this is what you can see on this graph. On the left, you have the PFAS concentration in the blowdowns, and on the right, you have the PFAS concentration in the site water. You cannot really see it clearly, but believe me, it's almost exactly the same PFAS signature. We find the same PFAS at the beginning and at the end. The concentration is higher for the blowdown because there is evaporation in the process because of the high temperature of the flue gas. 2 differences between in the PFAS signature between site water and blowdown. We have 6 FTS in the blowdown, but none in the site water. Maybe it's coming from an equipment in this incinerator, maybe it's coming from waste incineration, we don't really know. And we have GenX in the blowdown, but not in the site water. For GenX, we suspect it's because it's at very low concentration in the blowdown, so it should be even lower concentration in the site water, possibly below a method detection level, which is why we don't detect it in the site water. Same information here, just to compare in this graph, you can see in green the PFAS level set by the EPA regulation for drinking water, and the columns are the PFAS level in our blowdown. You can see that it's the same order of magnitude. It's PPT levels everywhere. Now let's move on to air emission results, which was like the most interesting for us. I am going to start with the baseline level. So on this graph, you can see the PFAS flow rate at the stack when we are not incinerated PFAS. This is OTM45 results. You can see that we have some PFAS emitted at the stack. And actually, it makes sense because the PFAS that we find at the stack, there is the baseline, it's the same PFAS that we find in the site water. And as I was saying before, the site water is contaminated with PFAS. It's in contact with the flue gas after the incineration process. Some PFAS go from the water to the stack gas, and then they are emitted at the stack. The good news is it's very low level of emission because we have very low level of PFAS in the site water. It's below 3 milligram per hour if we consider that non-detect PFAS are at the method detection level, which is a conservative approach. Now, what happens at the stack when we are incinerating PFAS? So we did multiple PFAS runs in the July and October campaign. and you observe two different patterns. Pattern 1, it's the most common. It's the one we observe in July and October. In this pattern, at the stack, when we incinerate PFAS, we found some low level of PFAS with less than 10 carbon. These PFAS, they are the same that we find in the site water. And then pattern 2, very different. We only observe it for 4 runs out of the 16, 17 runs that we did. So in that case, at the stack, we detect long-chain PFAS at a higher flow rate than in pattern 1. And the thing is, these long-chain PFAS that we detect at the stack, they are not present in the PFAS waste. We don't inject them in the incinerator. We don't really know where they come from. So when we received these results, we were really surprised. We discussed with AECOM, we discussed with the lab doing the PFAS analyses. And one explanation that we had is that somehow we had some field contamination during the PFAS sampling. We know that PFAS are everywhere. We have to be very careful when we want to sample it. So you can always have some contamination. Now let's focus on pattern 1. On the 2 graph, you can see the PFAS flow rate at the stack. The upper graph is for AFFF, and the lower graph is for soil. I will start with the AFFF. So in red, you have the PFAS emitted during the baseline. In yellow, you have PFAS emitted during AFFF incineration, and in green, it's AFFF plus slime. So first finding, when we incinerate AFFF, we can see a slight increase in the PFAS flow rate at the stack compared to the baseline. But if we add lime, we can see that the PFAS flow rate is significantly decreased. And the PFAS that we find at stack during the PFAS incineration are actually the same that we find in the site water. It's the same result for the soil. Now if we look at the table, so we inject in the incinerator around 10 grams per hour of PFAS, but when we look at what's coming out at the stack, we are in milligram per hour. So we have significantly reduced the amount of PFAS. So what we call the total DRE, destruction and removal efficiency, it's a comparison between what's coming out of the incinerator at the stack versus what was injected in the PFAS waste. And the total DRE, so it's on the sum of PFAS, so we are above 99.8 or 9 in each case. So we were really happy with this result. Just after, I'll show you the total DRE for each PFAS, not the sum of PFAS. Quick word about pattern 2. You can see on this graph the PFAS flow rate at the stack for pattern 2. Very different from what we have just seen. We have long-chain PFAS, not the PFAS that we detected in the site water, and at a much higher flow rate. And so, as I was saying, a possible explanation is a field contamination somewhere. Now I'll give you an overview of the destruction and removal efficiency that we obtained during the October campaign. I know this is a very big table with a lot of values. You just have to focus on the colors. In blue, we can see all the PFAS that were in the waste, but not detected at the stack. This is the best result we can hope for. You can see it was the case for a lot of PFAS. In dark green, we have 3 values in dark green for the PFAS. This is when we were able to reach a DRE of 99.999. This is a very high level of destruction. In July, we were able to do even better. I will show you on the next slide. So the main conclusion here is apparently in most cases we are able to reach a quite high DRE, above 99% for a vast majority of PFAS. We can also have a non-detect for a wide range of PFAS. Now in July, we also calculated the DRE, but this time we were even able to reach the 6.9 DRE, so 99.9999 for 4 PFAS. This is a significant difference with the October and July campaign, and this is because in July we were lucky to find an AFFF with a very high PFAS concentration. Because if you want to reach a very high DRE, you have to work with a very high PFAS waste. Because when we calculate the DRE, if we have non-detect at the stack, we still assume that the PFAS is present at the method detection level. So somehow you have to work with a minimum concentration to reach the 690 DRE. This is what happened during the July campaign. Now let's talk about PICs, so product of incomplete combustion. OTM50, it's a method developed by the EPA to look for short-chain PFAS, which are likely to be product of incomplete combustions. In this table, you can see in green all the runs where we had no OTM50 detected, so potentially no product of incomplete combustion. You can see it happens in a lot of cases, so this is a very good news for us. We had some OTM50 PFAS detected 4 times. Once it was PFAS with a 5 carbon detected during a baseline at the method detection level. Could be a false positive, could be a peak. And then we detected 3 times the CF4, the famous CF4. So I'm going to focus a bit on the CF4. CF4, it's an ultra-short PFAS, 1 carbon, supposed to be very hard to destroy. According to literature, if we want to destroy PFAS, to destroy CF4, we have to be at a temperature above the 2,500 Fahrenheit. This is not the case in our incinerator. We are working around 2,040 and 50. So we knew from the beginning we couldn't really destroy CF4 when we were injected in the incinerator. But yet, when we looked at the OTM50 result for the CF4 run, we discovered that the destruction and removal efficiency was of 43%. We were not really expecting this kind of result. We also detected CF4 in 2 other runs where we were not incinerating CF4 but AFFF. In that case, CF4 could be a peak of PFAS or even of another waste. But what we need to remember here is that in most cases, we have no peaks detected. Then for the solid sample results. So in this table, you can see in green all the runs where we had no PFAS detected in the solid sample results. We have 3 solids, ashes from the kiln, slag, and filter cake from the water treatment line. For 4 runs, we had some PFAS detected in the ashes from the kiln. Luckily, the PFAS level was very close to the method detection level, so we are talking ppbs here. So once again, what we need to remember here, in most cases, we have no PFAS or very low level of PFAS detected in the solid residues. So to answer the first 3 questions that we had in the beginning, the first conclusion is that based on the results that we've just showed, yes, high temperature incineration at Port Arthur is an efficient way to dispose of PFAS waste because we're able to reach destruction and removal efficiency up to the 6 nines for some targeted PFAS. We have also found out that we have very low level of PFAS in the liquid and solid residues. For the liquid, we have this issue with the fact that the site water is already contaminated with PFAS. But when we look at the blowdown, we see that we don't significantly increase the concentration of PFAS. We don't add new PFAS to what was already there. And for the peaks, we have shown that in most cases, we don't generate peak, at least we don't detect them at the stack. In terms of learning, so as I was saying, if we want to demonstrate very high DRE, 690 DREs, we have to work with very concentrated PFAS waste, not always easy to find. We had this issue with a suspected field contamination. So when you want to sample PFAS, you have to be very careful. Contamination happens easily because PFAS are everywhere, of course. And another finding that we made is that, sometimes we ask the lab to redo the analyses on the same matrix. And we could have significant results between the 2 analyses. There is a high uncertainty because we are working at very low level, like PPT level with PFAS, so it can increase the uncertainty of the measure. And a quick word about what we offer at Veolia. I have been focusing on the waste side, but we offer a wide range of solutions to deal with PFAS. So if you have any questions, come and visit us in our booth.
Hey, instead of waiting till the end, we've got a few extra minutes. We're going to go ahead and allow questions, 1 or 2 questions before the next presenter. Do we have a question for Flore?
So when you find low-level PFAS at the stack, you said that the signature is the same as the side water. How do you know, because you're burning the thing like crazy, how do you know the signature preserved after the incineration? After incineration, how do you know that's the side water?
I'm not sure I get it. So how do we know that the PFAS that we found at stack are from the site water and not the incineration?
Right. Why
Yes.
you say the signature is side water, the water you use from the site, not from the original waste?
Yeah, so it's possible that it comes from both. The baseline showed that at least the site water explains part of the PFAS that we detect at the stack. And when we compare PFAS flow rate when we incinerate AFFF versus baseline, we see a slight increase when we incinerate AFFF. So most likely, some of the PFAS we detect at the stack come from the waste incineration. There is 2 reasons why we have PFAS at the stack.
Okay, thanks.
I have one. I might have missed it, but what were the temperatures that you were using to get the 99.9999, which is a very good percentage there?
So it was always around the same temperature of 2040 Fahrenheit. It varies very slightly between each rinse.
Okay. Any other questions? Very good. We'll move on to the next presenter. Thank you, Flore.